So let's get started. We got a new unit here that we're starting, Unit 3. So we're starting in on a new chapter. This will sort of set the pace for what actually the rest of this semester and the next semester kind of looks like, where we introduce a functional group, we talk about properties of that functional group, and then reactions of that functional group. Okay? Alkenes are going to be our first functional group that has some interesting reactions associated with it. Previously, alkanes, we learned a lot about alkanes, but we didn't really have any reactions that we studied. Okay? So now we're going to talk about alkenes and alkene reactions, including mechanisms, which is why you have that review assignment that you're going to do, despite it being buggy as all hell on the last few questions, but try your best, all right? Cool. All right, so first of all, alkenes. What am I talking about here? An alkene is a molecule that consists of carbons and hydrogens, but we have at least one carbon-carbon double bond. Okay. In terms of polarity of this functional group, what do we think? This is going to be a polar or a non-polar molecule? Non-polar. We still only have carbons and hydrogens, right? So we still have a relatively non-polar functional group here. All right, so let's take a look at an alkene real quick. All right, so again, only carbons and hydrogens, but now we have a carbon-carbon double bond in there. All right, so let's rewind back to the beginning of the semester here. We talked about how bonds could be either sigma or pi bonds. So if I just have a normal old single bond in this molecule, which one is that, sigma or pi? Sigma, but then when I have a double bond, that consists of one sigma bond, but the other one is considered a pi bond. Okay, and all we really said about that was that we needed to know that double bonds consisted of one sigma bond and one pi bond, and then we didn't really go much further than that. Okay, so let's talk a little bit more about these sigma versus pi bonds here. All right, so what we're going to do is we're going to build this model for this carbon-carbon double bond here, which again consists of one sigma bond and one pi bond. Okay, what are bonds made of? Electrons. All right, and if it's a covalent bond, what do we say those electrons are being shared, right? So we have these shared electrons. Okay, so a sigma bond, which you're going to color in orange here, is a shared pair of electrons, where that pair of electrons lives directly between those two atoms that are being bound together. Kind of exactly what you would expect for a bond to look like, right? We got this pair of shared electrons. We're sharing this pair of electrons. It's being shared directly between the two of us, right? So again, a sigma bond means that that electron density is directly between the two bonded atoms. All right, so again, kind of exactly what you would expect here. A pi bond is also a sharing of electrons, all right, but the shape of a pi bond is really weird. It turns out that each carbon has this pair of electrons that's being shared above and below the plane of that atom. So in orange is a normal old, I'll get rid of this, try to make it a little bit less confusing here. In orange is my sigma bond, where that electron density exists directly between those two atoms. All right, but that second bond, that pi bond, is a little weird. The overlap of those electrons actually extends out above and below those atoms. Okay, so in a pi bond, that electron density extends above and below the two bonded atoms. All right, we talked about how alkanes were boring. They don't have any reactions. And all of a sudden, we throw a double bond in there, and now these are going to have some fairly interesting reactions that are associated with them. The reason for that is because when you have a double bond, you have this pi bond, and the geometry of that pi bond is really weird. That electron density is no longer just located between those two atoms, but it's actually extending up and below those atoms, which makes it really easily accessible from something else, right? You can get to those electrons a lot easier than you can sigma bonded electrons. All right, so this is going to be very important to the reactivity of this functional group. Why are double bonds so much more reactive than single bonds? All right, there's another aspect of alkene geometry that we want to note here. Let's take a very simple alkene, just 2 carbons here. All right, another thing that we reviewed at the very beginning of the semester was hybridization. What is the hybridization on this carbon right here in my alkene? So these are sp2 hybridized carbons. Both of them are, right? And what is the geometry of an sp2 hybridized carbon? Trigonal, planar. All right, and that planar word is going to be crucial. If I build the structure of this molecule here, right, each one of those carbons has this trigonal planar geometry. So all 6 of these atoms actually lie in one plane, right? If I did one slice, I would go through all 6 of the atoms in this molecule, okay? So about that double bond, we will always have 6 atoms that lie in a plane. In the case of this molecule here, it's quite simply these here. Right, so our carbons that are in our double bond, those are going to be in our plane. And the atoms they're directly bound to. All right, so that was a fairly simple molecule there that we were looking at. But even if I make it more complicated, I have a big alkene with many carbons in them. Right? Those single bonds I can rotate around. They're all spinning and such like that, right? But then you get to this middle region here with the double bond, and all of a sudden you hit like this flat area in your molecule because you have your 2 carbons about your double bond and the 4 atoms that they're bound to that all lie in this plane, right? So even though my single bonds can spin around, I still have that 6 atoms that lie in a plane there, okay? So why are alkenes so much more reactive than alkanes? It's both of these things combined. Number one, they got big old flat spots in them, right? Making them very easily accessible. You can get to this double bond, let me finish this off, or it's gonna drive me nuts. You can get to this double bond really easily because it's always going to be in this flat region of your molecule, right? Because of that sp2 hybridization and that trigonal planar geometry. Not only that, but once you get there, really easily accessible, you have this weird shaped bond here where you have a pair of electrons that extends above and below that flat surface in the molecule, right? So all that is to say that that pair of electrons is really easily accessible just by the shape of a pi bond and then the geometry of our alkenes because they're really flat in that double bond region, okay? So all of that is going to help to explain why our alkenes are so much more reactive than alkanes. So then real quick before we move on here, I'm going to draw a molecule, an alkene. All right, and you're going to highlight the 6 atoms that are all in a single plane here. All right, so I have my 2 carbons on either side of my double bond, and then the atoms that they're directly bound to, so that'd be this carbon here, and this carbon here. All right, but that's only 5. What's my 6th atom that lies in this plane here? The implicit hydrogen, absolutely, right? So there's this hydrogen sticking off right here that's implied, that is also in that plane. All right, so again, we can say our alkenes are flat. And then the other thing that's really important to note about double bonds, we talked about this a little bit before, right? But this also keeps that geometry, that planar geometry, is you cannot rotate about double bonds, right? So it's frozen in place there. You can't do any rotating, so all 6 of those atoms are kind of stuck in that plane. So we can just make a note, double bonds do not rotate. Cool. So we're actually going to save our explicit discussion of reactions of alkenes for next class. We got a little bit of groundwork to lay here first, and that is to start where we're pretty much always going to start with every time we introduce a new functional group. Don't get too excited, but we got some alkene nomenclature. All right, so let's just take an example molecule here. All right, now the good news is that if we have the basic rules down for nomenclature, all we got to do is tack a few new things onto them, right? So our broad outline here is going to be the same. We're going to find and name our parent chain. Step 1. All right, those prefixes do not change. Meth for 1, F for 2, prop for 3, et cetera, et cetera. Those are going to be the same, okay? But now we don't have an alkane, so we're not going to use the ane suffix. We have an alkene, and so we have this new suffix ene. Okay, so this isn't a butane, this is a butene. All right, then we're going to find and name any substituents. This molecule doesn't have any. All right. So now we're going to number our parent chain. Okay, so this is our first real functional group that we're introducing here. And because of that, we have to indicate the location of this functional group in our molecule. All right, so that double bond is going to get a number in this molecule here. So we got to number our parent chain, and basically same consideration as before. We want the double bond to have the lowest number. All right, so for my butene, I could say 1, 2, 3, 4, or go the other way, 1, 2, 3, 4, right? I'm gonna pick the red numbering scheme because that gives my double bond the lowest number. And how we refer to it in our name is by the lower number carbon. So this would be 1 butene, right? That implies it's between carbons 1 and 2. So our double bonds has, we're going to number, so our double bond has the lowest number. And we refer to its position as well. By the lower number carbon. All right, and then step 4, same as always, would be just to assemble the name. We don't have any substituents, so we're done here. All right, so this molecule right here would be 1-butene. Okay, so we got a new suffix for our new functional group here, ENE, and now we have this added complication where we actually got to indicate the position of that functional group in our molecule. All right, so I want you guys to do a few examples for me here. All right, so parent chain, these 5. Okay, if I number my parent chain, I'm going to go this direction here. All right, so this would be 1-pentene. Okay, same deal. 1, 2, 3, 4, 5, 6. Now I have a substituent, an ethyl group on there. If I number my parent chain, 1, 2, 3. I'm going to refer to my ethyl group, so this is 3-ethyl, 2-hexene. Okay, that location of the double bond will always go right out front of that parent chain name. All right, so let's look at 2 more examples here. Okay, so I want you to do the first 2 steps on this molecule. Whoops. All right, so if we find our parent chain, 1, 2, 3, 4, 5, 6, 7. This is a methyl group. This is an ethyl group. If we put in our numbers, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, this is where we're also going to have to update our rules. Normally, we would list all these numbers, and we would pick the numbering scheme that has the lowest number in it. Okay? Now we have a functional group in this molecule, and functional groups get what we call priority, meaning that the only thing I'm going to pay attention to when I pick a numbering scheme is the location of that double bond. I don't care about the methyl group. I don't care about the ethyl group. Only thing I care about is making sure that the double bond gets the lowest possible number. Okay? So if I was looking at the methyl group, I would want to pick 2, but again, we're not going to pay attention to the methyl group. Our double bond gets priority. I'm sorry, I would pick blue. Since our double bond gets priority, we're going to go with the red numbering scheme. Okay, so we got to update our rules here. Our functional group gets priority, meaning we're going to pick our numbering so that that functional group has lowest number. Turns out that all of the functional groups in organic chemistry are ranked, and you always pick the one with the highest priority to pick your numbering scheme. All right, in this case, we only know one functional group at this point in the semester, so let's not make our lives more difficult than we need to be. All right, bottom line is that that double bond in our alkene should have the lowest number. That's how we're going to decide what our numbering scheme is. Okay, so just to finish this one off, assembling the name, I'm still going to put them in alphabetical order, right? So this would be 3-ethyl, 6-methyl, 3-hexene. heptene. All right, so now take a second to copy down this molecule. Alright, so normally when we pick our parent chain, the name of the game is the longest continuous set of carbons. Right? If I'm looking for my longest continuous set of carbons in this molecule, it would be these ones here. The problem is that this excludes that double bond. And so again, now that we have a functional group in our molecule, we're going to pick the longest continuous set of carbons that contains that functional group. All right, so we got a little bit of a caveat to add on there. All right, we want the longest continuous set of carbons that contains the functional group. So to finish that, so everybody take a second and then finish this off here for me. What would be the name of this molecule here? So this would be 2-propyl 1-hexene. Okay, so these two represent our kind of, I think, the major changes that we got to make to our nomenclature scheme here. We're going to prioritize our functional group when numbering, and our parent chain must include that functional group. Functional group. All right, so I'm going to put down some examples, all right, and y'all work through these with our new considerations here. All right, so let's do this one here. Okay, I'm going to find my longest continuous set of carbons, but I know it has to contain these two right here, right? It's got to contain that functional group. My longest chain here would be these, what is that, 7? 2, 4, 6, 7 carbons right here. I'm going to find and name my substituents. I got 2 ethyl groups here. I'm going to number my parent chain, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. I want the one that gives my double bond the lowest number, so I'm going to pick the red numbering scheme. All right, so putting it all together, let me make some room. You need to move down. We would have 3,4 diethyl. Three heptene. All right, moving on to our next one. My longest continuous set of carbons. Also 7, very creative. I have an ethyl group here and 2 methyl groups. All right, if I number my parent chain, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. If I was looking at everything, then the 2 carbons on or 2 methyl groups on carbon 2 would win, but I'm only going to pay attention to that double bond when I pick my numbering scheme. So again, I'm going to pick my red numbering scheme. When I put my name together, it still has to be in alphabetical order. So this would be 3-ethyl, 6,6, remember you got to include both of them, 6,6-dimethyl, 3-heptene. All right, and then for our last example here, my longest continuous set of carbons are these, but I have to include that double bond in my parent chain, right? So that makes these my longest continuous set of carbons. So then I have a 1-carbon methyl group and a, 5-carbon pentyl group. And again, I'm going to number in such a way that my double bond gets the lowest possible number. So this would be 2-methyl, 3-pentyl, 8-octene. All right, and then for the sake of completion here, let's do one more. Alright, so my parent chain, I got 8 carbons. I got a propyl group and a methyl group. I'm going to number my parent chain. Alright, and so what's sort of unique about this one here is now there is a tie in my numbering scheme, right? Both my red and my blue numbering scheme puts that double bond on carbon 4. So if we have a tie, we're going to go back to our original numbering rules, where first we just want the lowest number in our name, and then second, if there's a tie, we'll break that with alphabetical order. Okay, so given that, see if you can't finish this off here, which one should be correct, red or blue? right? So this is actually now I would go back to my original numbering scheme. All right, well, neither of these two are going to be low. We have a 4 and a 5 versus a 4 and a 5, so that's not going to work. So then I have to go to the next rule here, which is our tiebreaker for alpha order, and methyl comes before propyl. So 4 methyl, 5 propyl, 4 octene.
So I see like there's kind of a carbon chain in the middle where the double bond would be at 2. Back to 1, 2, 3, 4, 5, 6. There's like a little like sort of 6 carbon chain in the middle.
Yeah.
So we wouldn't use that. We would use the
No, because that is not the longest chain that contains that double bond. So the only update to our parent chain rules, still looking for the longest one. The only caveat is it has to contain those 2 carbons that are about the double bond. You still want the longest one in there. All right, cool. So last thing we got to do here, we talked about how gravity works. All right, alkenes, right? Do not rotate about that double bond. So in this molecule here, I have a methyl group on one side sticking down and a methyl group on the other side sticking up. I cannot rotate this so that those 2 groups are pointed in the same direction. If I wanted to move that methyl group, I'd have to break these bonds here, right? Meaning that this is not the same molecule. I have now created a different molecule in order to move them to the same side, okay? So these 2 molecules that we were just looking at, they would have the same connectivity of atoms, but a different spatial arrangement, which would make them stereoisomers. Absolutely. So last thing we got to talk about are stereoisomers of alkenes. Okay, again, a function of those non-rotatable double bonds. So let's look at 2 examples here. Take a second. So these are 2 distinct alkenes here. Take a second to name these 2 molecules. All right, what's the name of the one on the left? 2-butene. And what's the name of the one on the right? 2-butene. But again, these are distinct molecules here, okay? So again, just like before, we got to build into the name this stereochemistry. All right, so first of all, these 2 groups are pointed on opposite sides of my double bond. Where on my other molecule, these 2 groups are pointed on the same side. All right, so we sort of had a designation for this before when we were talking about ring stereochemistry, and we're just going to recycle that again. When they're on opposite sides, we call them the trans isomer. Okay, so this would be trans 2-butene, and this would be cis 2-butene. Now, let's just look real quick, just to put down another very similar one. Okay, this would be 1-butene. Am I looking at the cis or the trans stereoisomer here? Or is that a trick question? It's a trick question, right? So this particular molecule here does not have any stereochemistry. Okay, so not all alkenes have stereochemistry. All right, and so how can I spy an alkene that does not have stereochemistry? One of those two carbons about that double bond are going to be bound to identical groups, right? So the fact that that carbon on the end is bound to two of the same things, two hydrogens, means that there is no stereochemistry associated with it. So no stereochemistry if one of those sp2 carbons is bonded to two identical groups. Right, so likewise in the molecule that we built, if instead there were two methyl groups on one of those carbons instead of just one, now all of a sudden we have a molecule that doesn't have any stereochemistry. If I flip it over, I get my other conformation, right? Cool. All right, so there's kind of a problem with this cis-trans stereochemistry. You'll hear it, but it's not like the official way of doing stereochemistry for alkenes. And that is because how would you deal with something like this? What if I had an alkene am I looking at the cis or trans isomer here? We can't tell using these rules for cis or trans, all right? So basically we're gonna have yet another set of rules that we get to apply to assign stereochemistry here, okay? So first of all, this is sort of the limitation of cis and trans. Cis and trans actually specifically would refer to hydrogens on our alkene, and so they only work for alkenes where there are hydrogens on each of the sp2 hybridized carbon. All right, so we can just note cis and trans only works if both sp2 carbons have one hydrogen. If those hydrogens are on the same side, it would be cis. If they were on opposite sides, it would be trans. But if you replace any of those hydrogens with another atom, all of a sudden that cis and trans goes to crap. Okay? So we have a similar but more expansive way of doing stereochemistry of alkenes called E and Z stereochemistry. Okay? So it turns out that trans 2-butene you could also call E 2-butene, and cis 2-butene you could call Z 2-butene. All right, so we had R and S for chirality. We're going to have E and Z for our double bonds. Okay, both types of stereochemistry, but not quite the same, right? An alkene doesn't have chirality. There can't be bound to 4 different groups. All right, so how do we assign E or Z stereochemistry? So step 1, we're going to chop at our double bond. All right, so I'm going to say hiya, right down the middle. Chop that double bond in half. Go to one side. assign high and low priority. Exactly like we did with our chiral groups here, okay? We're going to jump to one side of this double bond. You're going to do this one side at a time. I'm not looking at all four groups. I'm looking only on one side of that double bond. That's why step one is to chop. So I'm going to compare my chlorine and my bromine, and I'm going to assign one high priority and one low priority. Which one is the higher priority group, chlorine or bromine? Bromine. So bromine's high, chlorine's low. Okay. Now I'm going to jump to the other side. And assign high and low. So looking at this other side here, completely ignoring the first one, which is the high priority group, fluorine or hydrogen. Fluorine's high, hydrogen is low. All right? So then if both high priority groups are on the same side, same side is Z, and opposite sides is E. So looking at this molecule here, would this be the E or the Z stereoisomer? I got a high priority group pointed up and a high priority group pointed down, so they are on opposite sides. So this would be the E stereoisomer. All right, so you got to chop your double bond. You jump to one side, assign high and low. Jump to the other side, assign high and low, and then look at where your two high priority groups are. Okay? Again, if they're on the same side, it's Z. If they are on opposite sides, it is E. Okay? And just note, like I never compared my fluorine to the chlorine and the bromine, right? I'm not doing all four of these groups at once. I'm assigning high and low on one side, high and low on the other side. Okay? Now, sometimes, if you can remember the stupidest thing in the world, it will help you remember, and we have this for this. We can say that it is the Z stereochemistry if they are on Z, same side of the double bond. All right, so if they're on opposite sides, it's E. If they are on Z same side, it is the Z stereochemistry. Cool. All right, so then let's just finish up by doing a few examples here. I'm going to put down some molecules. You're going to name them, including the proper stereochemistry. so if I name this molecule without worrying about stereochemistry, this would be 3-hexene. Okay, but now I'm going to assign E or Z by chopping at that double bond. Okay, I'm going to jump to one side. I'm going to compare this ethyl group to what? Absolutely, that implied hydrogen that is on that bond, on that carbon. I'm again going to assign high and low. Which one's going to be higher, an ethyl group or a hydrogen? Yeah, so this one's high, this one's low. If I jump to the other side, I'm going to do the same thing. I'm comparing that ethyl group to this implied hydrogen. And again, hydrogen's always low. This one's high. Okay, so my two high priority groups are on opposite sides, so this would be which stereochemistry? E. Okay, and just like our chirality, it goes in parentheses out front, and then a dash to the rest of the name. All right, again, first thing I'm going to do is just name it without worrying about stereochemistry. This would be 3-methyl-2-pentene. I'm going to chop at my double bond. I'm comparing an ethyl group to a methyl group. Which one's higher priority? That ethyl group, so this one's high and this one's low. If I jump to the other side, I'm comparing a methyl group with that implied hydrogen. Hydrogen's always low, so it won't be high. So again, my high priority groups are on opposite sides, so this is the E stereochemistry. All right. If I name this molecule, 1, 2, 3, 3-ethyl, 3-heptene. And is this one the E or the Z stereoisomer? Boom, nice, yes, excellent. Whoever said it, somebody over there, was it you? Excellent, okay. How do I know that? Because I got this sp2 hybridized carbon that are bound to two identical groups, right? And you could figure it out if you went in there, you chop at your double bond, all of a sudden you're comparing an ethyl group to an ethyl group. Which one's gonna be high, which one's gonna be low? It doesn't make any sense, they're identical, right? So, in this case, we have a molecule that does not have any stereochemistry, so we would just leave it at 3-ethyl-3-heptene, right? No stereochemistry in that molecule. All right, and then this last one is also a 3-methyl-2-pentene. If I go and chop at my double bonds, my methyl group compared to my implied hydrogen, my methyl group is high, my hydrogen is low. If I go to the other side, an ethyl versus a methyl, my ethyl group is high, my methyl group is low. Now those two high priority groups are on Z same side, right? So this would be the Z stereochemistry. I promise it's dumb enough to just get stuck in your head right away, all right? And so we see here we got a pair of stereoisomers. Right? Two molecules that have the same connectivity of atoms. You can tell they got the same name, but they have different stereochemistry. One's E and one's Z. All right, so then just to finish this off here, we had said that this molecule here was E 3-hexene. I want you to take a second and draw me the Z stereoisomer of 3-hexene. All right, so how am I going to get the other stereoisomer? If I look at my E stereoisomer here, right, this carbon had that ethyl group, but then also that implied hydrogen. So if I want to get my other stereoisomer, I got to swap these two groups. All right, so I'm going to start it out the same. Now my next carbon bond has to be pointed up, and then I'm going to go from there. All right, and then lastly, let's look real quick. I'm going to get rid of those markings here. Which of these do we think is the more stable stereoisomer? Which one do we think is the more stable structure when those two ethyl groups are located on opposite sides, or when you put those two groups on the same side next to each other? Who thinks it would be the E that's more stable? And the Z that's yes, so the E, right? So big group, bottom, same principle we've used a lot. Big groups do not like to be near one another. So they would much rather be pointed on opposite sides of that double bond than forced onto the same side here. So our E is more stable because we have large groups pointed in opposite directions. All right, and we're going to see that this is a factor in reactions that produce alkenes. They like to produce alkenes where those big groups are located on opposite sides of one another as opposed to being right next to one another because it's just higher energy. Get some steric clashes between these two groups if they're forced onto the same side.